Verify that a necessary and sufficient condition for three vectors a, b, and c to be coplanar is the existence of non-zero scalars L, M, and N such that LA vector plus MB vector plus NC vector equals to 0. Okay. First, we will discuss the necessary condition. What is absolutely necessary for the above statement to be true? We will begin by considering that let the vectors A, B, and C, these three vectors, are coplanar. Now, what does it mean when we say that three vectors are coplanar? Three vectors are coplanar means that if we pick up any one of the vector, it can be always expressed as the linear combination of the other two vectors, x times b vector plus y times c vector, where we'll be considering x and y to be some scalars. Now, let's rearrange the terms. Here we have 1 multiplied to a vector plus negative x times b vector plus negative y times c vector equals to 0 vector. Now it has to be a 0 vector because here on the left hand side we are operating with vectors, so on the right hand side we must get a vector as well. Now this is actually similar to LA vector plus MB vector plus NC vector equals to 0 vector provided we choose LMN such that L equals to 1, M equals to negative x, and N equals to negative y. Now these are all non-zero scalars. Thus, if A, B, and C are coplanar, then there exists some non-zero scalar L, M, and N satisfying LA vector plus MB vector plus NC vector equals to the null vector. Okay, now let's discuss the sufficient condition. What is sufficient for the statement to be true? So, the sufficient condition is, let's say we have three vectors. We don't know if they're planar or coplanar or not. We're just going to consider three random vectors. So, let A, B, and C be three vectors. And we have L, M, N be three scalars. We're considering three vectors and three scalars such that, and these three scalars are going to be non-zero such that it's given that LA vector plus MB vector plus NC vector, that's it, this equals to null vector. So this is given to us. Then what we can do, we can consider LA vector to be equals to negative MB vector minus NC vector. Since L, M, and N, we are already considering it to be non-zero, we can divide each terms with L on both sides to get A vector equals to negative M over L B vector minus N over L C vector. Or we can say, we can consider A vector to be equals to lambda times B vector plus mu times C vector, where lambda and mu are scalars defined as lambda equals to negative M over L. And mu will be equals to negative N over L. So here what we have done, we have expressed the vector A as a linear combination of the other two vectors B and C. Now, we could have done it with vector B also. We can also express vector B as a linear combination of the other two vectors. Similarly for vector C as well. This means that this only tells us that A vector must lie. This particular condition just confirms that it must lie on the plane containing B vector and C vector. In other words, we are saying that A vector, B vector, and C vector, they must be coplanar. So this proves our problem. So we have derived both the necessary condition. The necessary condition is that we first started considering ABC to be coplanar, and we showed that it's given as a linear combination of LA vector plus MB vector plus NC vector equals the null vector, where L, M, N is given by this particular form 1, negative x, and negative y respectively. And the sufficient condition is that if we consider A vector, B vector, and C vector to be some random vectors with L, M, N being some non-zero scalars, then if this particular condition holds true, then it must be true that A, B, and C must be coplanar.